So calorimetry experiments, they're time consuming. When I did them at work, they were a good 20-minute reaction. So there are other ways to figure it out. Somebody's already done the work, so why not use the work that they've done, and we can figure out our enthalpy change that way. So it's a calculation, it's not an experiment, okay? And it looks at the individual reactions. So when we look at the decomposition of glucose, C6H12O6, and we get water and carbon dioxide as products, we look at those individual components of what makes those things up, okay? So same reactants can have different. So this here, the way that it works is that we add all the individual enthalpy changes of individual reactions to get a net reaction. Okay? This is where understanding your sign convention is really, really important if it's exothermic or endothermic. Okay? This is going to be really critical here. So you work backwards. You start with your net reaction, so this is the overall reaction that you're looking for. And then you manipulate the intermediate reaction, so the in-between reactions. So question number 8 had how many reactions required to make up this product. And it was, Mac and a couple people got it right. But it's those individual reactions and whether they're a forward reaction or a reverse reaction. Okay, so we're going to start manipulating reactions forwards and backwards. Okay? So it says here it could be reversed. If you have to reverse a reaction, you have to reverse the sign. Well, you'll see when we do an example, but you have to remember that part. So if the way the reaction is written is a positive enthalpy, but you have to reverse it to get the reaction that you want, you have to remember to reverse the sign. Okay, so this is going to require going slow through the questions and paying attention to sign convention. And then it says subtract, but basically you're adding a negative enthalpy. So subtract or add the reactants and products to get the net equation, and then you do the same thing for the enthalpies. So usually we use Hess's law when we have intermediate reactions listed and you want an enthalpy change for a desired net reaction. So this is what it looks like. This is what it looks like. So one of the methods that the steel industry uses to obtain metallic iron is to react iron 3 oxide with carbon monoxide as shown in the balanced equation below. This is what we want. This is our end goal. But it's asking us what is our enthalpy change for this balanced reaction. So it says use the following equations and their enthalpy changes. So we need to look at iron 2 oxide is what here? What is this side? Reactants or products. You only have 2 choices. This is a reactant, and this side is product. So what side is iron 2 oxide in on our balanced equation? On the reactant side or the product side? On the reactant side. This reaction here, where is iron 2 oxide located? On the product side. So we're going to reverse this reaction. Okay? And so right now, this delta H is now sitting at plus 1648.4 kilojoules because we reversed it. It requires a phenomenal amount of energy to break down iron 3 oxide rather than forming it. Okay, and then carbon monoxide, 1/2 oxygen and carbon dioxide. Well, we see carbon monoxide is on this side, so we're going to leave this reaction this way. I like to line up my arrows, just is how my brain works. Oops. you to look at our enthalpy. We didn't change this reaction around, so we're going to leave this as negative 283.0 kilojoules. Okay, that's the first step, is to line things up. Now, what is it that we want? We want 1 iron 2 oxide, or iron 3 oxide, and we want 3 carbon monoxides. So how do we accomplish that? Just straight up math. We want 3 carbon monoxides. Notice I'm multiplying the whole thing out by 3, including the enthalpy, because that enthalpy is for 1 carbon monoxide, and we need 3 carbon monoxides. What about iron 2, or iron 3 oxide, sorry? What do we need? We need 1 mole, but how many do we have the way it's written right now? 2. So we're going to divide this all the way across. We're going to divide it by 2. Okay? So our new line is going to look like this. 2 iron 3 oxides divided by 2 gives us 1. 4 irons divided by 2 gives us 2 irons. 3 oxides divided by 2 gives us 1.5, which we write like this as 3 halves. Make sure you're writing your states in. Your delta H, 1648.4 divided by 2 is
824.2.
positive. And then we look at carbon monoxide line. 3 times carbon monoxide is going to give us 3 carbon monoxides as gas. 3 times a half of an oxygen is 3 halves. And 3 times carbon dioxide is going to be 3 carbon dioxides. And our new delta H is going to be 3 times negative 283.0, which gives us what value?
Negative 849.
Okay. So our overall net, just show net by doing a double line. We're going to cancel out like terms. We have iron 3 oxide, but none on the product side. We have iron on the product side, but none on the reactant side. We have 3 halves of oxygen on the product side. We also have 3 halves of oxygen on the reactant side. So we're going to cross those off. So what are we left with? We should be left with and we double check it with our balanced reaction. Fe2O3 plus 3CO gives us 3CO2 plus 2Fe. So we've matched our balanced reaction. What's our delta H? Add these two together, 824.2 plus negative 849.0. So for this reaction to happen, our enthalpy change is negative 24.8. Is it exothermic or endothermic? It's exothermic. From there, we can draw a potential energy diagram. Okay? So our potential energy goes on the side, and it's measured in kilojoules. And our reaction coordinates go on the bottom. And it's an exothermic reaction, so is this a step up or a step down? Step down. So we have 3 COs. Right here we have 3 COs. And we're actually going to look at this part here. And so here we had 3 halves of oxygen. That's what we had there. Over here, we have 3 CO2s and Fe2O3 from up here. This one here. Okay. And so this one here has a big energy drop. Okay? This is delta H. Negative 283. Okay? And delta H equals negative, times 3, negative 849.0 kilojoules. Then we have this other part. We have the Fe and the other 3 halves of oxygen. So we draw a secondary line in here, like this. I'm just gonna, I'll put it here. Okay, there's a secondary line there where we have our 2 Fe's and our 3 halves of O2. And this delta H right here, this distance here in the green, 24.8 kilojoules. Okay? So we have to here. We have this energy drop too. So basically what we've done is we've superimposed 2 energy diagrams, one on top of the other, and this net here is what's left over when you're done superimposing. Okay? So this is the reactants on one side and the products on the other, but this ends up being a product when we flip it around. Okay, when we go back up to the original equations, Fe and 3O2 okay, this is the reactants from the original intermediate. And this is a reactant. Okay, those are the 2 original reactants. So then when we look at these, here, this is a product from the net reaction, and this is a product. So this line here is both a reactant and a product. One from the intermediate and one from the final. So it's a little confusing at first. We'll work through another one.
Can you scroll up to like on like the reactor like Fe2O3 to 2Fe as
Yep.
yeah. How did you find the delta H's for those two? Like not the top set but the bottom.
Here,
Yeah.
because I had to divide it by 2. So
So
then
you-
I have to take this and divide it by 2.
So what you did to your reaction to get the modified version, you had to do that to your changes in your delta H.
Yeah, that's why I put the bracket over here, the end
Okay.
bracket over here. The whole thing, the whole line gets multiplied by 3. Because this is for 1, and we want 3. Or this is for 1, and we want half. Okay? Let's look at practice problems. So it says, use the following information, or following reactions and enthalpy changes to calculate the standard molar enthalpy change for nitrous oxide when involved in the reaction. So this is our net one here, NO2, H2O gives us O2 and N2H4. So it's always easiest just to start with, we need NO2 on this side. So let's start with that one. I'll just write it here. So we want 2 NO2s. Now what have I done to this reaction?
You flipped it,
I flipped it, so what do I have to do?
you made your delta H negative.
Have to flip the delta H. Okay. This one here has water as a product, so we need to flip this one as well. So what do I have to do to my delta H?
Flip it.
Flip it, so it becomes what?
Positive 241.8.
Okay, and N2H4 is a product in our net reaction, and it's also a product here. So we have, I'm just going to write over top, N2, since I didn't change it, I'm going to leave my molar enthalpy alone. Now we need to balance this out. What do we see happening? We have 2 hydrogens here and only 1 hydrogen here. We also only have 1 water here and we need 2. So what do we do to this reaction?
Multiply it by 2.
Multiply it by 2. The whole thing. All the way over to the enthalpy. Okay? Anything else that we need to change? Let's just move this. I'm just going to move this down so we can see it a lot better. So we have so Jaden identified that we have to multiply it out by 2. So we're going to have our 2 NO2s. We'll have our 2 waters. We have 1 NH2, so let's see if it works out. This is all the products and all of the reactants put together. This is doing the ionic balancing, same as in Chem 20 when we did net ionics. This is the exact same thing that we're doing. We're just throwing enthalpies in. So here I see NO2 on the reactant side. I don't have NO2 on this side. Here I have 2 waters. I have no waters. Here I have an N2, and on this side I have an N2, so they cancel out. Here I have 2 hydrogens. Here I have 2 hydrogens. They cancel out. Here I have 2 oxygens and 1 oxygen. I know I'm going to combine those 2. And I have 1 dinitrogen tetrahydride. Okay, so that's my net balanced reaction, and when I look back up, I see that it matches. So now we need to figure out our standard enthalpy. So we have negative 66.4. We have 241.8 times 2, which is which? What do you get, Sam? 241.8 times 2? 3, you said? And here we have another delta H. So what do we have for an overall value?
That's what I got. I got 464.
Hang on a second.
Yeah.
To multiply this one
Yeah.
by 2,
Right in
that's negative, and that stays the same. Oh, so this is the overall net enthalpy for that reaction. It's asking us for NO2. So now we take this value here that we have for our balanced reaction. Do we get positive? And Jaden's saying he's getting a different answer, so what, is this correct, or
I got 464.8.
464.8? How many moles of NO2 are in this reaction, the balanced one? 464.8 divided by 2 is?
232.
Right? Because the original question is molar enthalpy change for nitrogen dioxide. So this is our final answer for number 1. Molar enthalpy. Okay, but we had to have this. We needed the net enthalpy change for the whole entire reaction first, because all we had were intermediates. Okay, so number 2 and 3, we're going to do Sam and Cameron are going to work on 2, and Reese and Sophia and Jaden will work on 3.